quality factor. Quality factor. So we have 2 months, March and April. In that, after February, we have very good time. We have. It's fine. Quality factor. It is the measure of. It is the measure of sharpness of the resonance. Sharpness of the resonance. It is the measure of sharpness of the resonance of an LCR circuit. So what is a quality factor? Quality factor is measure of sharpness of resonance. That is also called Q factor. Q factor is quality factor. Q factor is given by voltage across L or C. L or C along the inductor or along the capacitor, whole divided by voltage across R. Voltage across R. So in fact it is given by VL or VC. One of the thing you have to consider, divided by VR. This is what you have to consider. So it is given by the formula. Q factor is given by the formula 1 by R into square root of L by C. Q factor is given by the formula 1 by R into square root of L by C. So definition wise, how do we write? So formula you have written, everyone? So how do we write the definition wise? How do we write the definition? We'll write the definition like this. So it is actually, it is defined as the ratio of voltage developed across the inductance or capacitance at resonance to the impressed voltage impressed voltage means VR, to the impressed voltage. Impressed voltage means voltage across R. This is how we define the Q factor. This is the definition of Q factor. Quality factor. Once again, we'll write the definition. Q is equal to either VL or VC divided by VR. Okay. It is given by another formula 1 by R into square root of L by C. So it has no dimensions, no units, no units, no dimensions, no dimensions. It is just a number, just a number. It is just a number. It is just a number. So it's a dimensionless quantity. Dimensionless quantity. It is a dimensionless quantity. Once finished, please let me know.
Noted, sir.
Okay, now another thing. Now we have, it is also called, it is also called voltage multiplication factor. It is also called voltage multiplication factor of the circuit. This is the other name. It is also called voltage multiplication factor of the circuit. If R value increases, Q factor decreases in a circuit. Why? We have the formula Q is equal to 1 by R into square root of L by C. This is the formula. So from this formula, you can understand that Q is inversely proportional to R. R increases means the Q factor will decrease. Clear? Next one. Larger the Q factor, larger the Q factor, thus electronic circuit, the electronic circuit would respond to a very narrow range of frequencies, to a very narrow range of frequencies. Larger the Q factor, the electronic circuit will respond to a very narrow range of frequencies.
Noted, sir.
Okay, good. Now, larger the value, larger the Q value, sharper the resonance peak. Resonance peak. Okay, so this is what you had to see. So this is I versus omega curve. Current versus frequency curve is what we check. So this is a broad one for a low Q value, little bit sharper and even more sharper. So this resistance, if I consider this is R1, R2, R3, definitely we will understand that R1 greater than R2 greater than R3. Lower the resistance, larger the Q value. So this is the funda. Lower the resistance, lower R, larger Q. Larger Q. This is the funda which you have to understand. So you get sharp resonance curves will obtain at lower resistance. At lower resistance. This one, if you remember, this is fine. So when I see sharper and sharper curve, that is the case where I get lower resistance. Please note it.
Noted, sir.
Okay, ma. Right. Very good. Now, the next one. The Q is also given by another formula, omega R divided by omega 1 minus omega 2. Omega 1 minus omega 2. Where you know what is omega R? Omega R ante resonance frequency, where omega 1 and omega 2 are frequencies when current decreases to decreases to 0.707 times the peak value of the current. The peak value of the current. The peak value of the current. Omega 1 can be written as omega R plus delta omega, and omega 2 is omega R. Omega R means resonance frequency minus delta omega. This quality factor test is done at the resonance frequency. Please understand that. That is most important. Difference, if you find what is omega 1 minus omega 2, that is 2 delta omega. This is the difference. Omega 1 minus omega 2 is 2 delta omega. That is the difference of the frequencies. This is called bandwidth of the circuit. Of the circuit. This particular thing is called bandwidth of the circuit. So we can write Q is equal to omega R divided by 2 delta omega. This is measure as measure of the sharpness of the resonance. Measure of the sharpness of the resonance. Measure of the sharpness of the resonance. So another definition of Q factor is Q factor is the ratio of the resonant angular, okay, I should say the angular resonant frequency. Angular resonant frequency. Angular resonant frequency to the bandwidth of the circuit, to the bandwidth of the circuit. So we can write the funda, smaller the bandwidth, larger the resonance. Larger the resonance. Smaller the bandwidth, larger the resonance. Written this.
Written, sir.
Okay. Now, this is another question can come. What is the significance of Q factor? What is the significance of Q factor? So this is what we'll see. Q factor denotes sharpness of tuning. Q factor denotes sharpness of tuning. This is the first point. Point number 2. High Q factor indicates lower rate of lower rate of energy loss. High Q factor indicates lower rate of energy loss. That's one thing. High Q factor indicates high Q factor indicates high Q factor indicates sharper peak in the current. Sharper peak in the current. High Q factor indicates sharper peak in the current. These are the things what you have to know.
Noted, sir.
Okay, ma. Now the next one. Average power associated in an AC circuit. Average power associated in an AC circuit. Average power associated in an AC circuit. So how do we do that? We know power is equal to dW by dt. We know this very well. And now from this, we know that power is also E into I, where E is the instantaneous voltage, I is the instantaneous current. So you know E is equal to E naught sine omega t. Like this we'll consider, sine function we'll consider. And I is equal to I naught sine of omega t plus phi. We have the current and voltage are have a phase difference of phi. That's what we consider. Now with this we know that we can substitute these things. So dW by dt. What is W? Work done, that is. So that is E into I. E into I. This is how we can do. So we can do that dW is equal to EI dt. We can write this. And now we can integrate on either side. This is the full cycle integration 0 to t. So up to here you can write.
Noted.
Okay, good. Now the work done is given by, we will substitute integral 0 to t ei dt. So we can do integral 0 to t e naught sine omega t into multiplied by I naught sine of omega t plus phi. This is what I get. So dt is what you get. So E naught into I naught is what you get. Integral 0 to t sine omega t into sine of omega t plus phi dt. This is what you get. And now this integral we have to evaluate. This integral can be evaluated in many ways. So one is like you can multiply and divide with the 2. This is how you can evaluate. Of E naught into I naught is what you get. Integral 0 to t. So This is like you can write it as cos of a minus b into cos of a plus b. So a minus b becomes cos phi, and the a plus b part becomes cos of 2 omega t plus phi, simply. Cos of a minus b minus cos of a plus b is 2 sine a sine b. So from that formula, I have written this straight away. This is dt. So please note up to this point. So this we can put a bracket over here. Entire thing is coming into brackets.
Noted.
Okay. Now let's clear this thing. So what we're calculating is the work done first. Work done in the circuit. So it is half E naught into I naught. We got. So here this cos phi is common. The cos phi is a constant. So here I get the integral 0 to t cos phi dt is first part minus half E naught I naught integral 0 to t cos of 2 omega t plus phi. This is what I get. So dt. We have to evaluate this integral as well as this one separate. So we'll do that. Now, so cos phi is a constant, so it will come out of the integral. So integral 0 to t, so this becomes half E naught I naught into t cos phi. This is what you get here. And now minus half E naught I naught. This one becomes, so you can give an integral substitution. 2 omega t plus phi is a some L or something you can give. So 2 omega dt becomes dl, right? So dt becomes 1 dl by 2 omega is what you get. So simply this entire thing is nothing but cos L dl divided by 1 by 2 omega. So let's write 1 by 2 omega. So I'll get sine L. So that is nothing but sine of 2 omega t plus phi under the limits 0 to t. The beauty is this one vanishes to 0. Why you had to tell me? See, it's very simple. Omega t, what is omega t? That is 2 pi actually. What is sine of 2 pi plus theta? So I will tell you here this integral alone 1 by 2 E naught I naught. Let us write 4 omega, no problem. Here anyway this vanishes to 0. So when I put the t, so we get sine of 2 omega t, right? So you get sine 4 pi plus phi minus sine phi is what you get. Sine of 4 pi plus theta is sine phi only. So this integral vanishes. Sine phi minus sine phi, that is 0. The integral vanishes to 0. So manaki migilin integral enti idokate. This is what we are left with. So the answer here half E naught I naught t cos phi is what you are left with. That's the work done. So you send the t onto other side, so you are left with W by T. That is the power, right? That is half E naught I naught cos phi. This is what is the average power. This is what is average power. This is what is average power. Now we have a little bit we have to do one small manipulation. Clear? Return this.
Yes, sir.
Okay, good. Now we'll see. The next part is, see, average power we got half E naught I naught cos phi. This we can write it as E naught by root 2 into I naught by root 2. Root 2 into root 2 is 2. So we'll write like this. So we'll write cos phi here. So I naught by root 2 is what? ERMS. I naught by root 2 is IRMS. So multiplied by cos phi. Here this cos phi is having a special name called power factor. And phi is phase difference between voltage and current. IRMS, you can say IRMS and ERMS. ERMS. So this is how you get. And now what else we have? The power factor cos phi is defined as P average divided by ERMS into IRMS. IRMS. It's also written as true power divided by apparent power. True power divided by apparent power. And also cos phi. From the triangle, you can say it is R by Z. Which triangle I am talking about? Phi. This is the triangle. Remember. This is what is your R. This is XL minus XC. This is Z. Z is equal to square root of XL minus XC whole square plus R square. And this is the angle phi. This is what we are talking about. Yes, Amma, sufficient today. So rest of the things we will see 1, 2, 3 concepts. Rest of the things we will see later. And again, later we have 1 or 2 concepts and then transformer. With that, this chapter will be completed. Maybe 2 more classes, it will be over. 2, 3 classes, that's it. It will be over. And after that, we'll see what can be started. We'll have a discussion on that and then we'll start the next part. So is it okay? Can I clear?
Clear, sir.
Okay,
Yes, sir.
Okay, we'll meet tomorrow. This is sufficient today. Bye.
Thank
See
you,
you
sir.
all.